There are a few technologies that mark out key points in the history of the computer. These are keystone events that set the stage for the future. I'm talking things like the EDVAC report, which leads to a recognizable form of stored programmed computers, or the launch of the IBM PC, which sets in stone what home computers would look like for decades to come, or IBM's System 360, which pushed us into the 8-bit byte as a standard. If any of these events happen slightly differently, well, the story of the computer would be very different indeed. One of these keystone events happens in 1972. That's the creation of the C programming language. Almost every programming language in modern use is somehow related to or influenced by C. It's how curly braces become popular. It's why, if you know Python, you can pretty quickly pick up JavaScript. It's the root of so many current lineages. I think you'd be right to say that if C never happened, programming would look and be very different. Then, what could programming have looked like without C? Now, that's really hard to say. C becomes a phenomenon for a number of reasons. However, there were a number of languages that were developed around the same time as C and had very similar design goals and purposes to that of C. These were high-level system programming languages, tools meant for writing operating systems and compilers. These powerful compromises between the control of machine code and the flexibility of a high-level language. C itself evolves from some of these earlier attempts, but there are separate lineages here unrelated to this popular language. It's easy to imagine a history where C is developed but never takes off, where it's killed in the cradle by one of these unrelated systems languages. In that case, the future of programming may have taken on aspects of the victor, that is, if we assume that this one fight in the 1970s leads to modern programming. If we follow that assumption, then looking at C's competitors could give us a glimpse of that alternate future. Welcome back to Advent of Computing. I'm your host, Sean Haas, and this is episode 148, Is Bliss Ignorance? This episode will be taking a look at a failed language. Now, I will say, a lot of failed languages aren't that interesting. There are some that are just idle passing fancies. There are some that are just amateurish. Not cool except for maybe a little pointing and laughing, but even that's in bad taste. This language, however, I think stands closer examination. The language we'll be discussing today is called BLISS. It was developed in 1969 at Carnegie Mellon University. It was intended as a portable systems programming language. It was derived from ALGOL. It competed directly with C, and it lost. What I find interesting is that the goals of BLISS align almost word for word with the goals of C. The key difference from the outside is that C was developed at Bell Labs. But there must be some deeper difference here, right? Why did BLISS fall to the wayside as C rose to prominence? Was it a matter of place and time, or was BLISS somehow missing a killer feature that made C a winner? In this episode, I want to talk about BLISS as its own language, but at the same time, I want to work out what made it different. Why was it considered a competitor to C? What did BLISS do that was better than C? What made it worse, and how did it eventually lose? In doing so, I hope we can work out a few things about good program language design. But for this one, I'm going in totally blind. So who knows? Maybe it's that C is the bad language and BLISS was wrongly overlooked. Why does that matter? Well, it all comes down to the power of C. Most modern languages are somehow related to C. If you've ever seen a language with curly braces, chances are it is directly related to C. The life of a modern-day programmer is very deeply shaped by choices made during the development of the C programming language in the early 1970s. That makes the idea of a counterfactual pretty darn exciting. What if C failed? What if it was different? Or what if it was beaten out by an entirely different language? That language very well could have been BLISS. Now, before we get into the episode proper, I have actually 3 announcements this time. The first is that I'm currently in the process of working up a bonus episode over on Patreon. Right now I have a thread up where I'm taking suggestions for a bonus episode for, I think maybe another week, maybe 2 weeks, depending on how active it is. I'm then going to take the 3 most popular ideas in that thread and put it to a poll for the patrons. There's still a little time to get in on deciding the bonus topic. For that, you can head over to my Patreon. All right. Announcement 2 is that on February 8th, I'm going to be speaking at Intelligent Speech. This is an online conference for history podcasters to get together and give talks on a specific topic. This year, the topic is deception. It should be a lot of fun. I spoke last year and had a great time. So if you want to join in on that, you can get tickets at intelligentspeechonline.com. And announcement number 3 is that I'm going to be at VCF SoCal this February. I know, I'm making the rounds for once. VCF SoCal is happening February 15th through 16th in Orange, California. It's right near LA. You can actually fly into Burbank or LAX and get over to the conference pretty easily. That event is taking place at the Hotel Faro, which is a big conference center. If you want to attend that, you can actually get special room rates through vcfsocal.com to stay in the same hotel and walk right down to the convention floor. It's actually a really, really nice setup. Right now, I'm planning to give a talk on some software restoration at VCF SoCal. I'm also going to be milling around the conference all weekend. So if that sounds fun, I'd love to hang out. Come show up, we can meet up, and we can have a great time. That, once again, is happening February 15th and 16th in Orange, California. Okay, all of that done, so let's start the episode itself. Computer programmers are a little, well, let's say dramatic. That might be the most reasonable word to use here. I think this has something to do with how programming kind of warps the human mind. Because of that, we tend to get some pretty spicy papers and letters to the editor of various journals and magazines. One of the all-time greats in this genre is Edgar Dijkstra's go-to statement considered harmful. The paper hits print in 1968, and as Dijkstra puts it, quote, "I discovered why the use of the go-to statement has such disastrous effects, and I became convinced that the go-to statement should be abolished from all higher-level programming languages." End quote. Dude doesn't like the go-to, and he argues that you should also hate it. But what exactly is the deal here? The go-to on its own is a pretty innocuous concept. It tells a program to jump to some predefined label. You label some piece of code, then you tell the program, hey, you remember that part of the program I told you about? It's time to go to that. It's that simple. This is a very low-level way of thinking about programming. It's actually how computers think. On the processor level, most logic is built out of a series of what are called unconditional jumps. That's the exact same as a go-to. This is backed up with some conditional jumps, which are like having a go-to inside an if statement. Early on, many high-level languages also supported this type of jumping. Fortran, for instance, lets you run a go-to. BASIC is, perhaps, famous for its use of the go-to statement. On its own, a go-to is fine. Well, on its own with a label around, but you get the idea. Where we get into dicey territory is once we start looking at everything that can be around the go-to. For a very simple program, a jump is fine, it's just a jump. What you often want is to only execute a part of a program if some condition is met, and otherwise execute some other part of that program. For that, you can chain together some if statements with a few go-tos. If the light is green, then go to the label called start. If the light is red, then go to the part of the program called stop. Very simple. But what happens if, say, you have a go-to in a more complex program? Let's say, by way of example, you have a loop that contains a go-to statement. How should the language handle that? You're basically terminating that loop early and going to some other part of the program. That's perhaps a little strange, but we can probably all work up a solution to that problem, right? You're just exiting that loop a little early. But what happens to variables inside that loop? What happens to the scope of variables when you jump? What happens to global variables that have been modified when you jump outside a loop? You get into all these tricky gotchas that you have to think about and plan around in the language. Now let's flip that example. Let's say you have a label inside a loop. Then you jump to that label. You're jumping right to the middle of a loop, effectively entering the loop from the side. But it's not that simple. Loops all have to start with some kind of setup routine. It's usually just a header that says, do this while x is less than 10, or something similar. If you jump to the middle of a loop, then you are, in effect, entering that thing prematurely. The setup hasn't been done. So, what happens? If the loop is supposed to run 10 times, but you jump into the middle, does it run 10 and a half times? What if the loop assumed that x would start at 0, but you're jumping from some point where x is 1,000, or x is minus 10, or x is some other non-numeric value? Suddenly, you have to design a pile of edge cases, or build out a robust error handling system, or maybe have go-tos that can jump anywhere, but no, not actually there. You have to have some restrictions. Go-to Considered Harmful was published in Communications of ACM and quickly became a hit. Over the years, it's become something of a meme amongst programmers, but its core idea is sound. Go-to was implemented in most languages prior to 1968, and it introduces a host of problems and inconsistencies. This isn't to mention things like optimization, which becomes almost impossible if you don't know the flow of a program. One of the people impacted by Dijkstra was one Dr. William Wolf, who, at the time, was a researcher at Carnegie Mellon University. As Wolf would later explain in an oral history interview, quote, "I bought into that and decided we should design this language, BLISS, without the go-to statement. It was clear theoretically that you could do without it as long as you had other control structures like if, then, else, and then various iteration statements and subroutine calls. But it wasn't clear that as a practical matter, that was going to be a good idea." End quote. Now, to be 100% clear here, there were already some languages without go-to statements. Lisp and its family offer one example. That said, Lisp-like languages have always existed kinda in their own world. They're purely functional, which is a totally different approach to design. Most other languages, from Fortran to Algol, from BASIC to PL1 to COBOL, used the go-to. The idea of a language built without go-to that wasn't a Lisp relative was an enticing line of inquiry. But that wasn't Wolf's only motivation. The Dijkstra paper would serve as something of a jumping off point to get Wolf into a larger project he had been considering. In the same period, there was a hot debate over programming operating systems. This is sometimes called systems programming, that is, very complex code that sits close to the computer itself. The key argument was, should operating systems be programmed in high-level languages? For the 1960s, this was high controversy. It was traditional to write operating systems in assembly language or machine code. This was done at first because you just didn't have any other options. High-level languages don't really appear until the late 1950s. When they do, they aren't very well suited to systems programming. Why wouldn't a high-level language work for this application? It all comes down to control. Systems programming requires very precise code and total control over the computer. You have to do things like juggle registers, move around blocks of memory to precise locations, and handle physical interfaces. The whole point of a high-level language is to pull the programmer out of all those mundane details. A language like Fortran was designed to protect you from all sorts of low-level nasties. But it's that exact nastiness that you have to face when you write an operating system. This leads to what seems like a paradox. High-level languages are meant to stay out of the low-level realm of the machine. So how do you use a high-level language to write low-level code? What's even the point of attempting such a feat? There are a lot of good reasons to break from tradition and use a high-level language for this kind of software. I know this from experience. I've written a few very bad operating systems in my day, in both assembly language, a low-level language, and C, a high-level language. When you work in a high-level language, you can use less code to do the same thing. Fewer lines of code means fewer bugs, and it means that the bugs you introduce are easier to track down. You also get access to much more sophisticated features. This varies language to language. For me, the jump from assembly to C gave me reusable data structures, data types, and actually visible pointers. That's not to mention that high-level languages are just more readable and easier to maintain. By 1968, there were a number of projects that were attempting to make this jump. Burroughs had an operating system written in a dialect of Algol. So did GE. There was also the ongoing Multics project, a full time-sharing operating system written in PL1. We're solidly in the emerging phase of this technology, and Wolf wanted in. Sometime around 68, he started his plans for a new operating system. The first step, though, was choosing the high-level language to use. After a survey, he landed on an exciting conclusion. None fit his criteria. As he would later write in his first paper published on BLISS, quote, "We have chosen to add to the tongues of Babel by defining yet another new language, and some justification is required. The only valid rationale for creating a new language is that the existing ones are inappropriate to the task. It was our judgment that no existing language dealt with all the proper issues, and hence a new language was necessary." End quote. The go-to list aspect being front of mind made its way into the list of requirements. I honestly think that might be one reason that Wolf really chose to create a new language. All the competitors had go-to. The rest of the list has to do with systems programming, pure and simple. But keep in mind, this was an emerging field. There wasn't some traditional and enshrined set of requirements for this kind of language. There is plenty of space for discovery here, which is what makes these kinds of times so exciting. Here I'm going to be cherry-picking from some of Wolf's line items, because in his paper on BLISS, he gives a straight-up list of design requirements. That's really handy to use. The first item, and probably the most obvious, is, quote, access to all relevant hardware features. To do systems programming, you need to have some way to control the system. That's a simple enough idea, right? But what does that mean in practice? This usually means allowing some kind of direct memory access. Yet again, memory is the heart of the computer. But this isn't just to let you push around bits and make funny little images. Many computers represent I/O devices in memory, or have special structures in memory for setting up things like interrupts or data channels. So if you have fine-grained control over memory, you have nearly total access to the hardware of the machine. That's the route that BLISS would go. The next line item is that a system language should have no need for runtime support. What does this mean? Well, most normal languages are targeted to run under something like an operating system. That means that the code, once compiled, expects certain tools to be ready and waiting for it. If your program prints something to screen, it's using runtime support. It's calling out to the operating system while it's running and asking for a little help. But what happens if you're the operating system itself? What if you are the clown Pagliacci? In OS land, you have no runtime support. You have to bring your own runtime support. You have to make yourself laugh somehow. So a systems language cannot rely on runtime support. That means you won't find things like print in BLISS. You have to work out how to do that yourself. The next item is control of representation. This goes hand in hand with hardware access. When a computer offers memory mapped stuff, that doesn't just mean location matters. It also means that structure matters. An IBM PC, for instance, wants a very specifically formatted table at a very specific address for setting up interrupt handlers. How does control of representation help this? What does that even mean? Think about this in terms of data structures. If you have control of representation, then you can define data structures with a very specific pattern in memory. Then you can create a structure that matches that PC's interrupt table. You could graft that table from the computer's spec sheet into your language and then manipulate it using your language. Sometimes you'll hear this concept, the representation of a data structure, called its shape. At least, that's the term I use at work. Those are the straightforward and obvious line items, but the list keeps on going. This is where we pass into more innovative territory. The first is modularity. That is, chunks of code can be compiled into modules that can later be loaded by another program. On one hand, this is just practical program design. Modularity lets you reuse little helpful programs that are already compiled and ready to grab. You just take the binary, plug it into your new program, and you're ready to go. Now, the documentation around modules in BLISS is a little cagey, and I don't want to go down the route of learning and working with BLISS right now, so I'm going to guess. The reason I said that modularity is an innovation here is because I think BLISS can pull a trick with modules. Keep in mind, this is from reading papers and spec sheets and extrapolating based off what I've seen in similar languages. I think BLISS should be able to do dynamic module loading. At least my understanding points to BLISS having all the features needed for dynamic modules. That means that while running, a BLISS program could grab a module from disk, load it into memory, and plug it into a running program. How BLISS handles communication in and out of modules, plus some of the weird stuff about its pointers, make me think that that kind of module loading would be pretty simple in the language. But hey, this is my guessing. There'd be a lot of actual support you'd have to write to do that. Now, the next design feature is conditional compilation. This one is also weird. The general idea is that you have some way to control what the compiler chooses to compile. You can put in some special code that, given some information at compile time, will either be included or excluded from the final program. On the surface, why would you want that? You always want all your code compiled, right? Well, not necessarily. The most simple case here is debugging code. It's common to have a complex debugging library built up that helps you debug your program. That can take up a lot of space and add features that only you as the programmer need. When it comes time to compile and ship your program to users, you don't want to include all your debug code. With conditional compilation, you can just tell the compiler to ignore that part of the program. Thus, your dirty secrets are kept safe from prying eyes. BLISS takes this a step further. It introduces this concept of a compile time code and runtime code, as in code that's executed while the compiler is working and code that's executed when your final program is running. This is something that we don't have enough time to get into, sadly. The short story here is that BLISS has a very, very sophisticated macro system. It's so complex that you can write an entire program only using macros. That's, like I said, very complicated. It's something I'm choosing to gloss over in the interest of time. Now, the last item I want to hit on is actually a sublist just titled Overall Good Language Design. I mean, yeah, sure, all languages should have overall good design, right? The details here are pretty standard, things like readability and well-structured code. I want to just drop one thing from that list that I think is particularly interesting. Quote, economy of concepts, generality, flexibility, end quote. To me, that sounds like a concept we've talked about before. Orthogonal design. The idea was core to the design of Algol 68. In short, in orthogonal design, you try to have a minimized set of primitives in your language that you use together to build up the rest of the programming language. To do this, you need to pick simple primitives that can work together. Algol 68 is very, very orthogonal. Like I said, it was a core design goal. BLISS isn't quite at that level, but the language has that orthogonal feel to it. In fact, in later papers, Wolf even mentions that he was trying to go for an orthogonal design. Now, there is one other secret design goal. That's machine independence. That right there, that should set off some alarm bells. How do you make a systems programming language that can be independent of the underlying system? Besides the paradox that introduces, it also puts BLISS on a direct road to conflict with another language. But that conflict is still a few years off when Wolf decides on these design goals. When you write an assembly language, the main thing you're actually programming is memory manipulation. You might have some cool game or tool in mind. You might have some neat algorithm you want to implement. But at the end of the day, the majority of your assembly code is just pushing around bits and building data structures in memory. When you're down in that low-level world, you don't get much help with, well, really anything. One of my favorite realizations came a few years ago. I usually write assembly language for the PC without any sort of runtime environment. I prefer the bare metal, as it's called. That means no Microsoft DOS, no real libraries, nothing. Well, I decided to write my first DOS program a few years back, still in assembly, of course. Now, DOS offers some useful runtime support. It will print to the screen for you. It will read and write files from disk, all the classics. What it doesn't give you, however, is any kind of help pushing around bits. Even with DOS's runtime, you still have to manually handle memory. I remember realizing that, chuckling, and going back to my bit bashing ways. Yet again, memory is key. This is why it's so crucial. It's such a big deal when a language supports data structures. I personally like the dumb bean counting I have to do in assembly language, because I don't do it professionally. It's a fun little hobby to do, like how some people paint minis or work on a car. But when it comes to actual programming, it's a pain. It's error-prone, it's annoying, and it's very difficult to do correctly. When you jump to a high-level language, you can just have, an integer variable or a string or something more complex. That's a huge leap forward. You don't have to worry about the beans anymore. All this is to say that data structures are very important. Variables and types are very important. BLISS has no data types. It's what's known as a typeless language. What's interesting is that I can only think of a few other typeless programming languages. You have Forth, BCPL, B, and this weird cursed thing called plan calcul. To say it's an uncommon choice is an understatement. Typelessness is rare, strange, and wondrous to behold. This gets weird quick, so I want to start from basics. I know I keep calling back to the Zeus episodes, but I can't help it. Zeus has managed to worm into my brain. So to everyone that said I should have covered Zeus much earlier, you were right, you win. Now I'm cursed. In plan calcul, Zeus's programming language, there's only one data type, the bit. You start from there and you're expected to build up data structures by composing bits. That might make a structure called an integer that's composed of 32 bits, and you might treat that like a whole number. But the language itself has no enforcement of that structure. It has no concept that an integer is 32 bits. That enforcement part is crucial here. That integer structure that you create isn't anything special to plan calcul. There's nothing stopping you from treating it like a 16-bit structure by accident, or a character, or something else that would make no sense at all. BLISS's type-free system works in a very similar way. It's not that you have no types, it's just that you only have one. In BLISS, that's the so-called full word. It's, well, just as it says. It's whatever the host computer uses as a word of data in memory. For the PDP-10, for instance, a full word would be 36 bits. When you define a variable, it's allocated as a single word. You just get 36 bits. You, as the programmer, are expected to use those words as building blocks to make more complex data structures. If you read up on BLISS, one thing that's stated over and over again is that interpretation of values isn't related to the variable, but to the operators you apply to that variable. That's one way to deal with types, I guess. What that means is that instead of BLISS knowing, say, the difference between adding integers and floating point numbers, you have to use special operations for each case. BLISS comes with an addition operation that can handle full word integer values, but no concept of what adding a decimal point means. If you want to do that, you need to write an operation or function that could treat a variable as a decimal and handle the actual math itself. There's no language level enforcement. The rule of thumb here is just don't write nonsense code. And yes, we should always strive to produce correct code. That goes without saying, but the lack of support here feels, well, it feels more than a little bit concerning. If we stopped here just with the typeless variable system, then we'd be in quite a strange spot. BLISS would be a high-level language where you have to do assembly-style bean counting to handle data. What makes this even more strange, and perhaps, once again wondrous, is how BLISS handles pointers. I have to get a little technical here, so be warned. Pointers give a high-level language a way to talk about where data is stored in memory. That's crucial for any language like C or BLISS that has to precisely control what's in memory. That goes back to the point about hardware control. In most languages, an assignment is defined to be something along the lines of symbol equals expression, where symbol is some valid variable or pointer or some named thing, and expression is any valid code that returns a value. An assignment will take the value from that expression and put it in that specified symbol. It makes an association. BLISS defines an assignment as expression equals expression. Confused? Concerned? I was both when I saw that definition. The reason this works is that in BLISS, an unadorned variable is treated as a pointer, as is the left-hand side of an assignment. If you see a variable named x, that's actually a pointer that points to some full word in memory. You have to do a special operation to get the value that pointer points to. In other words, when BLISS sees an assignment operation, it evaluates the first expression, the left-hand side, and treats that result as an address in memory. Then it evaluates the second expression, the right-hand side, and stores its results in the specified address. This means you can do wacky and wild things like telling BLISS to store 1 in 1. That's just 1 equals 1. Or that x plus 1 equals 2. That would be valid code. Now, I ask you, how does that make you feel? I would assume that for many practitioners, this should feel scary. Maybe it makes you mad. Like I said, this confused me at first. Why would you write a language like this? Well, dear listener, as I've learned more about BLISS, I think I've started to like this idea. But just to be clear, my point of view is a little twisted from exposure to bizarre programming languages. By allowing for expressions on the left-hand side, you open up a world of possibilities. The big one is indexing. I want to reach for a real-world example here. To do that, I want to introduce another feature of BLISS. To get the value of a variable, you use the contents of operator. It's just a period. So you have a variable named x. Then x on its own is just a pointer to memory. But .x is the value that's stored at that address. On computers like the PC, you have a special region of memory for graphics. In text mode, this is just a chunk of memory that holds character data. To print to the screen, all you need to do is store a character somewhere in that region of memory. If you want to print a string like hello world, you have to use a loop. You start at the beginning of graphics memory and place the H. Then you move to the next address in memory and the next letter in the word and print E, and so on. One way to do this is to set up a pointer at the base of graphics memory, and then increment the pointer as you jump through the loop. That's a very common solution in assembly. But BLISS offers another way. Since you can use a left-hand expression, you can write to memory with an offset. If you're inside a loop, you usually have some value, usually called I by tradition, that says how many times you've gone through that loop. You can just say something like memory plus I equals whatever next character you want to print. I think the actual expression you'd want to use would be graphics memory plus .i equals string plus .i. That would synchronize little indexes, and by running that through, you just print hello world to the screen. That may sound subtle and pretty technical. The point here is that BLISS's strange pointer system gives you more ways to solve problems. It gives you different ways to solve problems. At the same time, it introduces something funny. That offset trick I described is another commonly used idiom in assembly language. In fact, the whole expression pointer business is pretty common in assembly. This is a case where BLISS, once again, is acting like a low-level language. To be clear, this is a shared quirk amongst all system programming languages. You have to find some way to balance high-level features and hardware control. BLISS does it with this strange type and pointer system. You have the ability to use low-level tricks inside a high-level language. But it's not just doing the same thing as assembly. BLISS is actually a market improvement here. The offset trick is a good example. In assembly language, you have very limited ways you can use offsets like that. You're usually restricted to offsets by constants or offset math using specific registers. You get a little flexibility, but not much. In BLISS, however, you can do any kind of math you want. You could call a function on the left-hand side. You could do a division operation or a modulo. In that sense, BLISS brings a whole lot of power to this lower-level practice. Okay, so that's the most basic core of BLISS. From here, it continues to unfurl. I said that BLISS had a certain orthogonal feel to it. By that I mean all its features work with each other to build upon each other. So let me unfold the next petal. BLISS is an expression language. That means that the smallest unit of code is an expression, as in everything evaluates to some value. That makes sense in most cases. 2 plus 2 is an expression that evaluates to 4. As we've seen, .x is an expression that evaluates to the value of a certain address in memory. But everything is an expression. So x equals 1 is also an expression. that happens to evaluate to the number 1. In general, BLISS has evaluation rules for everything. That includes if statements, loops, declarations. It's everything, every construct in the language. If you write a line of code, it will return some defined value. This is in contrast to statement-based languages like Fortran or C or Python or most other languages out there, actually. An assignment in Fortran doesn't have a value. It just tells Fortran to run an assignment. You can't say x equals if blah. That would be nonsense. But in BLISS, an if statement is just an expression. And an assignment is just an expression, an equal sign, and an expression. Once again, the language is able to really work well with itself. So far, this should all sound pretty interesting, if not a little miserable. As I said, one of the big benefits of a high-level language over assembly is data management. Everything I've already covered, especially the centrality of the word, puts BLISS just slightly above the level of assembly. You have some nice tricks with expression assignment, but not a lot more. What kicks things up a notch are structures. Now, of course, BLISS has to do this its own way. To get this part to have the proper impact, I have to jump forward a little bit and touch on the elephant in the room. I've been trying to hold off talking about C, but to explain why BLISS's structures are so strange, I just gotta do it. In C, a structure is a way to define a custom data type composed of multiple values. Suppose you're writing a program that deals with data on a grid. You'd want to have some way to represent a data type for a point on that grid. You could just make a new structure, name it point, and say it's composed of 2 integers named x and y. You can make new variables of type point and easily access and set their x and y values. When you define a structure, you're also defining its layout in memory. Our point structure takes up 8 bytes in RAM, 4 bytes for the x value, followed by 4 bytes for y. Every new point will take up the same amount of space and have the same layout. This is one of the ways that C handles precise hardware control. You can use structures to talk about memory in a high-level way. C structures are, for lack of a better term, declarative. You declare you have a new struct named point, and you declare what it looks like. BLISS's structures are usually described as algorithmic, but I think it would be more in line with the theme of the language to call them expressive. In BLISS, you define a structure by specifying its access pattern. You name your struct, a list of arguments, and then an expression that uses those arguments. That is, on a fundamental level, pretty different than how other languages handle structs. Right away, something like the point struct is out the window. You don't have named members in BLISS. The most basic example is an array of words. For that, you'd make a new structure, call it array, and say that it took 1 argument. Let's call the argument I, since it's tradition. The access expression would be something like array plus .I. That does the pointer math needed to get the ith element of the array. Then you could make an array and access it just like in any other language. Since the access expression can be any expression, you can describe very complex data structures. You can make multidimensional arrays or trees or anything. What's crucial and what's so different here is that you aren't defining the shape of the structure. Rather, you're defining how you calculate locations within the structure and how big each element is. You define code, not memory patterns. That's very, very different than other languages. If I had to go out on a limb, I'd say this reminds me more of assembly than anything else. When I write assembly, I tend to write either macros or small helper functions to retrieve or set data. If I'm working with, say, a list, I'll write a function to get and set list elements. That's vaguely similar to the approach BLISS takes, but not quite the same. BLISS lets you actually bind the structure. those access expressions, to variables, so the language treats those variables in a special way. Now, I think that should do it for the entire data part of BLISS, and let me be clear here, the data part is really the strange part of the language. Once we get to things like loops and scope and conditionals, stuff settles down quite a bit. A big reason for this is that BLISS is based off ALGOL. Many languages, including C, are related to ALGOL at some juncture. It's where we get a lot of modern rules for things like block structure and scope. That's why a lot of languages look vaguely similar. BLISS is no exception. It uses blocks of code marked by beginning and end exactly like an ALGOL. Lines end in semicolons, just like an ALGOL. So the general shape of the language is somewhat familiar to the programmer. By 1970, the first version of BLISS was ready for use. Now, the matter of platform here is important. The first BLISS compiler was developed at Carnegie Mellon for the PDP-10, made by DEC. In the next few years, it would become a somewhat cross-platform language as long as you were on a DEC computer. In fact, BLISS would become what seems like DEC's favorite language. For this part of the story, I'm pulling from Roland Brinder's paper, The BLISS Programming Language, A History. There's a good paper, but do note if you seek it out that Brinder writes in the third person in some spots. That tripped me up for a while, because Brinder himself was the one that brought BLISS to DEC. It all starts in 1970 when Brinder met Wolf and was introduced to this strange new language. By that time, BLISS was already running on DEC hardware. There was also active work to adapt the language to a new machine, the CMMP. This is a whole topic in and of itself, so let me just touch on it and move on. The CMMP was a research machine under development at Carnegie Mellon. It was one of the first big multiprocessor systems, and its operating system called Hydra was written in BLISS. BLISS was already showing some promise at CMU. Brinder explains in his history that at that point, the language had been used for a number of utilities on the PDP-10 and, crucially, a compiler. This was supposedly a quote-unquote what-for-like compiler. I know, vagaries upon vagaries. This takes a second to unravel, but it's worth it. At this point, BLISS is self-hosting, meaning that its compiler was actually written in BLISS itself. But remember, BLISS is a bit of a weird language. It has a pile of idiosyncrasies, and its compiler is somewhat unique and complicated. So, what is what for and how does it factor in? Simply put, it was a third-party Fortran compiler written at the University of Waterloo. Now, I'm going to make an assumption here. When Brinder says what for like, I'm assuming he means that this mystery compiler handled Fortran code. This is a little tenuous because what made what for special is that it pulled a few tricks so you could immediately execute a Fortran program after compilation. It could be that Brinder meant someone wrote a similar tricky compiler for some other language. But I'm guessing it was for Fortran because that makes the next step more logical. Either way, by 1970, there are two compilers written in BLISS. One of those is for some non-BLISS language. Brinder learns about the language, gets a demo or two, and becomes a convert. To quote, "As the BLISS compiler stabilized, Brinder turned his attention towards introducing its use at DEC. Fortunately, a new optimizing Fortran compiler development project, known as Fortran 10, was starting at a good time to use BLISS 10. As compiler and language-oriented people themselves, the development team was eager to use a high-level language for their work, as well as being perhaps less risk-averse than others regarding the strange new language from CMU. The Fortran 10 group plunged into using BLISS and never looked back." End quote. A note on notation here. It was common to name DEC software after the version of PDP computer it ran on. So Fortran 10 was for the PDP-10, as was BLISS 10. Once BLISS moved into DEC, it really became cemented. According to Brinder, there was some resistance in the larger community of DEC users and employees. He says it came to a head at a DEC user group conference, DECUS, when attendees started wearing buttons that said, "Bliss is ignorance." That sounds like a great story, and apparently it's true. I can't find images of said pins, but there are contemporary accounts of this slogan showing up at user group meetings. This animosity was eventually tamed once Fortran 10 came out. It proved to be a capable compiler, which made a lot of detractors retract their position. Future DEC projects would rely heavily on BLISS all the way up into the VMS era. So then, why was there so much pushback? That's one of those things that's hard to quantify. Period arguments get muddied by later speculation. In 1971, as BLISS was making its debut at DEC, C didn't exist. There wasn't a clear frontrunner in the field. In fact, there were very few options when it came to high-level system programming languages. As mentioned way at the top, you had a dialect of Algol, PL1, and maybe BCPL if you were in England. The most basic reason for resistance comes down to the classic argument. None of these languages can be as powerful as assembly. This is the same argument that John Backus faced way back when he started developing Fortran. In that case, programmers didn't want to try a high-level language because of concerns over performance and precision. If you write an assembly or machine code, you have full control over everything the machine does. With a compiled language, the compiler decides what the machine does. You have to give up a little control, which is hard to do. By 1970, the performance argument had been blown out the water. A generation of programmers had been raised with high-level languages by that point. But the precision part of the argument, that was still leaned on specifically in systems programming. That kind of code does need a high level of precision after all. So there are some valid reasons to argue. The main critiques I've seen about BLISS come from after C is introduced. I found quite a few interesting threads from Usenet that discuss issues with BLISS in the 80s, and a few mentions in some papers and mailing lists. One strangely period argument that I did run into actually comes down to GoTo. Remember how that was a core design goal? BLISS was initially envisioned as a language without any form of GoTo, something to make Dijkstra proud. According to some, that was handled poorly. Listen to this from 1975 in a paper titled "Structured Programming Considered Harmful." Quote, "It is interesting to see what happened in BLISS, a language whose designers eschewed the GoTo because, in their view, it was redundant. They were forced, as a consequence, to introduce 7 new statements." End quote. The paper goes on to list the 7 different forms of exit statements used in BLISS. And this is actually true. In BLISS, there are 7 special expressions for exiting blocks, loops, conditional statements, functions, and a few other constructs. It's one of those weird quirks of the language. You can't just go to some location outside of your current block. You have to exit. But since BLISS supports nested blocks, an exit can, in some cases, be ambiguous. Do you want to exit from the loop you're in, or from the case statement inside of it? As a result, you get a weird set of specialized exit calls. But that's more nitpicky than anything. The vast majority of arguments against BLISS come down to its data handling. This even comes from within CMU itself. In 1972, Wolf co-authors a paper called "Reflections on a System Programming Language," which discusses lessons learned a few years into using BLISS. One of the critiques is the danger of pointers, especially as implemented in BLISS. This was a known issue by the 1970s. Pointers are very powerful, but they introduce whole classes of possible bugs. If there's nothing to check where a pointer is pointing, then you could end up pointing back at yourself. In some languages, that could be avoided. Just have the compiler throw an error if you point into a dangerous direction. But BLISS lets you do all kinds of weird runtime tricks with pointers. You can make a pointer on the fly. What happens when pointer math, which can be very complex in BLISS, goes wrong? Well, we already knew the consequences. Folk were doing similar tricks with pointers in assembly language. BLISS made the tricks more sophisticated, but the same type of pointer math was common on the lower levels. When you made a mistake, you'd get a particularly nasty and hard to spot bug. I know because I've made those kinds of mistakes. Most recently, I wrote some bad code that accidentally pointed to a return stack. It took me at least a day to figure out what was wrong. BLISS's pointers are very powerful, but they can also be very unstable. There's also the matter of type. This is one of the largest arguments against BLISS in more modern discourse. Typing makes a language safer. What do I mean by that? By enforcing data types, you prevent a lot of accidental and just stupid bugs. In a more strongly typed language, you can specify that a function must be given a number, for instance. That prevents you from, say, trying to add a number and a character and getting unexpected results. Or perhaps trying to do some pointer math and accidentally adding two irrelevant values, resulting in some nonsense pointer directed out into memory space. There's one other big issue that comes up in any critique of BLISS. That is portability. One early design goal was machine independence. Now, in theory, BLISS as a language could have been portable. There's nothing very machine dependent about the language as such, or so it would seem. There are some specific details about its data type, the full word, that cause issues. BLISS 10, the first compiler, used a 36-bit word. That meant code written for BLISS 10 assumed that each variable would be 36 bits wide. The next compiler, BLISS 11, was written for the PDP 11. That machine had a 16-bit word, so a full word in BLISS 11 is 16 bits instead of 36. There were also changes in how pointers were handled because the PDP 11 handled addresses differently than the PDP 10. The result is that code written for BLISS 11 isn't necessarily compatible with BLISS 10, and vice versa. Eventually, DEC codified a so-called common BLISS, a standardized dialect that was fully portable. But that didn't happen until the latter part of the 1970s, and it was only really used within DEC. The language was kind of trapped. Then we get to the real elephant in the room. In 1972, a language called C is developed inside Bell Labs. In 1973, Unix is rewritten in that language. In 1976, Lyon's commentary on Unix is published, which is used extensively in university classrooms. The book uses Unix's source code as a case study in programming, carrying C along with it. I personally think that once the commentaries are published, it's a little too late for BLISS. Unix spreads quickly after that point, as does C. The spread of the language is, of course, much more complicated than that, but I think that's a reasonable summary. The C programming language was developed with many of the same design goals as BLISS. It was meant to be a systems programming language. It was designed specifically to be used in Unix, an operating system. C has pointers, but they're slightly safer than the full throttle pointers used by BLISS. Both languages are inspired by ALGOL, so the syntax is even similar. The big difference, what nearly every argument boils down to, is typing. C has variable types. BLISS does not. That means that C is, right off the bat, a safer language. At least somewhat. It's still kind of dangerous with how it handles pointers, but, potato potato. On a technical level, C is less error-prone than BLISS. But it's able to do most of the same things. On its own, that doesn't necessarily lead to a winning language. The final factor is availability. The spread of Unix is tied to the spread of C. You can't get one without the other. As more and more mini computers start using Unix, that means more and more users have access to C. the C compiler comes along with every version of Unix. And since Unix was initially distributed as source code, every Unix installation came with a pile of C code to look at. By entering Unix, you were entering the world of C. BLISS, on the other hand, never had that kind of availability. DEC used a lot of BLISS, but the BLISS compiler was never generally available to the outside world in the same way as the C compiler. That, paired with its shortcomings, made it a much weaker showing than C. And I just don't think there is ever any getting around that. Alright, that does it for today's episode. We've seen how BLISS emerged, what made it unique, and what made C better. Does this mean that BLISS is a bad language? Is BLISS truly ignorance? I'm tempted to say yes, but I've learned better. My saga with Track has taught me to judge languages a little less harshly. BLISS is a very unique language, especially for a high-level language. It represents this snapshot in time when we didn't have very good tools for high-level system programming. Sure, there are parts of its design that are flaky, dangerous, and perhaps annoying. However, there are reasons for those choices. It's not just an amateurish system, it's not just something to point at. It was built to solve a very specific problem, and good choices were made for a lot of its design. C isn't just a better language than BLISS, it's not that simple. There are many features of C that are better than equivalent features in BLISS. Take the entire data handling parts of these languages. The complication here is that BLISS may be better suited for representing some types of code. You can just solve problems in different ways in BLISS because its variable system is so different. I'm also saying this because BLISS has kind of charmed me. It's an interesting language that I'd actually like to mess around with. To that end, there are modern compilers. Notably, OpenVMS comes with a BLISS compiler, which you can actually get hobbyist license for now. That program was canceled for a while, but it's back, so if you want to play with OpenVMS as a hobbyist, you can do that for free. FreeVMS also has a BLISS compiler from what I've read. There's also the BLISS-M compiler, which is an open source project. I've been playing around with that one myself. You can compile BLISS-M on Linux, so it's easy enough to use. Right now I'm trying to link some BLISS to an entry point written in C so I can try to boot a computer into BLISS. Gonna see if that actually goes anywhere, maybe a fun weekend. The point is, if you want to take the plunge, there are tools and resources out there. Thank you so much for listening to Advent of Computing. I'll be back in 2 weeks' time with another piece of computing's past. If you like the show, there are a few ways you can support it. You can tell your friends. Word of mouth is a great way to help grow the show. You can also rate and review the show on Apple Podcasts and Spotify. You can support the show directly by signing up as a patron on Patreon or buying merch from my merch store. Links to all of that are on my website, adventofcomputing.com. Right now on the Patreon, as I mentioned in the top, I'm in the process of picking the next bonus episode. That process is going to go on for a few more weeks, so if you want to get in on that, please go over to my website, go to the Patreon and sign up. It costs as little as $1 a month. And as always, have a great rest of your day.